Welcome everybody and the tutorials of Unit 5. Today we will talk about the collision model. For any chemical reaction, in order to start or to initiate, it has to collide. The particles of the reactants must collide first, and this collision must be in the proper orientation with sufficient amount of energy. So if we just come here to this type of reaction in here, so if you look at this reaction, you can see that we have a molecule of O2, which is represented in red, and carbon monoxide, okay, they're colliding right now. So the first condition is applied. But if we look at the direction of their collision, they're colliding in improper way. Okay, and that's why you will have no reaction at that point. On the other hand, if the molecules of oxygen and CO collide, but at that point it will collide from the side of carbon, then this is the proper orientation. And as a result of this process, you will have a product. We can see that they're colliding with sufficient amount of energy and the proper direction or orientation. So these are the most important factors in order to have a product in your reaction. Let's go to the definition of elementary reactions in section 5.4. Generally speaking, in order to have a reaction, they should collide. So if we introduce you to a concept of elementary reaction, you have to describe that it's a process in a chemical reaction that occurs in a single step. So the single step is represented by the definition of elementary reaction. We have only one reactant, which is A. At that point, since you have only one molecule, which is A, we can say the molecularity of this reaction is unimolecular, which means one molecule in reactants. And if you want to write the rate law for this step, what you have to do is, and what you have to do in this point and rate law, it's represented by the rate constant in addition to the concentration of A that is raised to the power 1 because you have only one molecule of A. Let's take the second one. The second one contains two molecules of A, and you can represent them in terms of 2A gives a product, right? So at that point, how can I write the rate law for that point? Since you have 2 here for the A, then the rate law is going to be K multiplied by the concentration of A to the power 2 because the stoichiometry of A is 2 in here, and that's why it should be raised to the power 2. And since you have two molecules, at that point you have two A's, then we have to call it bimolecular. The molecularity for this reaction is bimolecular. You could have two different reactants. For example, you have molecule A and molecule B. So you have two species at that point. And that's why, since you have two reactants species, then it's a bimolecular. And if you want to write the rate law for that, you're going to say it's KAB. In both have a second order of reaction. Now, let's introduce you to the last, which is the highly unlikely types of reactions in which you have three reactants that should react at the same time. They should collide at the same time in a proper orientation with sufficient amount of energy, which is very rare case. But it takes place, but so rare. Now, if you have a termolecular, the molecularity here is termolecular, which means that you have three reacting species. So you have A, or you can represent it in terms of three A's to give you a product, which means that you have three particles or molecules or species of air colliding with each other. Or it could be AAB or ABC, never mind, as long as you have three reactants or three species. And these are represented in terms of the third order. So the third order reactions are very rare because you need to collide these particles when a proper orientation is a sufficient amount of energy, which is very, very rare case.